Let's have a go. First part, composite functions. What is a composite function? Can I please have, let's go with Rachel. What is a composite function? I would have knocked out someone already last time. All right, next one. What's a composite function, Zan?
It's a function within another function.
Yeah, very good. It's a function within another function. Give me an example of a composite function, Jack.
Log e of x squared.
Log e of x squared. Very good. Log e of x squared is a composite function. You have log e of x squared. We don't know if it's defined or not, but we know it is a composite function. Give me another one, Phoebe. 1 on x squared. Yes, you can call that a composite function as well. This is a 1 on x squared. What else can I have? Let's go with Aiden. Give me another one. Say it again. X root x squared.
What the hell?
X root x squared. This is a mixture, actually. This is a product of functions with a composite function in there. So the composite function would be x squared within the square root, and then x multiplied to that, that's product of functions. Okay? So it's a product of a composite function, and yes, you're right. These two can cancel and simplify, but you can't always just cross it off and simplify. Why is that? With composite functions, why can't I just take off the square root and the square? What do I have to be careful of? The domain. You see, when I cross off the square root and the x squared, this now tells me that I've got x. Why is it a problem? It's because x, which is a linear equation, it can have negative numbers. But logically, normally, square roots, you can't have a negative number. Okay, you can't have a negative number in that. But in this particular composite function, you can. Why? Why can you have a negative number in this particular function? Because it's squared. Because it's squared. Because if you put a negative value in, you'll always get squared and it becomes positive. Because it becomes positive, it doesn't matter. Okay? And remember, this all falls under the point of what I was trying to say, the definition or the condition for a composite function to work. We're looking at the range of the function has to be a subset of the domain. And that one works. You see, if I drew an x squared graph, this is what it looks like. The range of this graph here, range of f, is equal to 0 to infinity. This happens to fit in, 0 to infinity actually fits in, it's a subset of the domain of a square root function. What's the domain of a square root function? I draw a square root function, that's a square root function. What's the domain? 0 to infinity, so they both fit. Because they both fit, that's why the definition makes sense, where we say range of the first function has to be a subset of the domain of the second function. That's why. Okay, we're just saying it has to fit. The range of this graph, the y values have to fit the x values of the second graph. If it does, then the composite is defined. So in this case, square root of x squared does work. And you get a function. Okay, you get a defined composite function. All right, and that's once you can define it, then you can simplify it. Okay, now you can say, oh yeah, we're just the same as x. Okay, but you can't simplify it before you define a domain. You have to make sure it works first before you simplify it. Okay, and that's a classic example of that would be something like this. Oh, so if I gave you that, you simplify it. Yes, it works, but what have you taken away? See, if I sketch this graph, this is going to be different to the graph you would sketch if I had simplified it first. If I took x squared divided by x, it becomes x, straight line. It's a linear equation, but what's the problem with a linear equation is that the domain can be any value. But logically, if you were actually to type this in, you can't have 0. 0 would make it undefined. So that's why they're technically two different graphs. They give it to you like this. Before you simplify, you have to check, do the domains work? And that technically is a composite function. Okay? All right, here we go. We got, what is a composite function? We got some examples. What does G and the little O, F mean? How do you read this? Jason?
G
Good, very good. This means g of f, which means g, and you're substituting the function f of x. That's why when Zahn said a composite function is a function within a function, that's what it is. It's f of x is within g of x. That's why that's the range of f of x is the subset, because it fits into the domain of g. You're substituting it in, so it becomes the domain. Yeah? Next part, what conditions are needed, which I just told you in this particular case, it was range of your f of x, which is your range of your f function, has to be a subset of the domain, which is what you're substituting in, and you're substituting into the domain of g of x. That's the condition, composite function. Okay? Last one. So you had two conditions to work with from chapter 1. One, does the range of the function fit the domain of g? Okay, that's the first step. But the next question, usually in a sort of SAC or an exam, most students will forget this part. What is the domain of g of f? How do I find the domain of g of f?
It's the range of.
So you got a composite function. So the ones that you just gave me are when we had, what was it again? Log e of x squared. What's the domain of that?
The domain of f.
Yes, it is. Because whatever you put in, so remember, how do you understand composite functions is you can think of it as two processes. F of x is what you're dealing with first, then whatever f of x spits out, that's what you're going to put into g of x. Remember that when I drew two machines? So what you're putting into f of x is called the domain. You put in a number, so you put in 1, goes into f of x spits out a value, which is the range, hence range of f has to fit the domain of g. That's what this is saying, yeah? Now, when you put in x, that's the domain. Whatever x can take, or whatever x can be, that obviously affects g of f. So that's why the domain of g of f is actually just the domain of f. Whatever you're putting in, that's domain, and this is the range of g of f. That's the logic to it, so if you forgot it. But that's just revising their composite functions for exercise 7b. How do we feel? Pretty good? Well, now you can do an example. Okay? So I want you to do, I'm going to give you about, how many, that's 4 questions there. I'll give you 5 minutes. I want you to find the domain range of both. I want you to find which one of these two exist. Okay? And then the function that doesn't exist, I want you to make it work. So if it doesn't exist, how do you make it work? Which means that the range of f has to be a subset of the domain of g, or the other way around. The range of g has to be a subset of the domain of f. Okay? C, and then find the domain of f of g and g of f if they exist. So in C, you would have restricted it so that it works. Now they both work, what is the domain of both graphs? Okay? And these are your equations. F of x is 1 and x, and g of x is root of x minus 3. I want you to answer that. I'll give you 5 minutes to do that. Okay, so you just look at what are the conditions. Just looking at the graph, you've got a rectangular hyperbola, and then the next one, you've got a square root function, translation to the right by 3. Figure out the domain, find out the range. If you can visualize it, part A is easy. Part B is using definition of composite function. When does it exist? Part C is now that you know it doesn't exist, and make it exist. That's the hardest part. Part C is what you want to learn from your exercise books. And then part D, once you've done the hard part of C, then D is just finishing it off. Who's coming tonight? No one. Yeah. What's your name?
It took me a long time trying to like J.
So it would be today. It did take you a long time.
Yeah.
The first one. I thought I'd just do it now and then that's it. Let's go back and say, Mr. Tran said this. I'll record it too. But I was right though. I said for year 12, it reduces significantly for term 3. I've only got 2. For today. Most of it they come from year 7s. And then year 11's got 8 out of 24.
Because the teachers are like, whatever.
Too late by now.
It's too late, like beginning of this was good.
Usually that's how it is.
Yeah.
For I have revision sheets. I don't know if they're practice sats, but I do have revision sheets to print out. Should be available tomorrow. I'll give it to you tomorrow, then you got weekend, and you come back. Yep, that's the definition of a modulus function. Well, that one. Sorry, I thought you were talking about this. It's one of that. Oh, yeah.
Oh, wait. Oh. This one.
So that's the thing, that's what we asked. And the tricky part is they said he's not explicitly, so he's an implicit. So, and that's where they didn't really answer me.
So say like you do have something like that. Do I have to sketch throughout?
Yeah, no, they want to ask you to sketch.
But like say
Oh, wait,
like
sorry.
your method of how is there an easy way of knowing it's gonna so say if it was I'm sure you would have the example, but then I'd be like,
Yeah, the thing is, you are not required to know how to apply modules. So if they give you a graph and say find the module of that, they won't do it. But what you are required to know is what means, really. Okay, so it means that it's going to make it positive. So if they gave you a question where they had mod of degree 3, you may know that it's
say, but in that,
yes. That's what I'm saying. That's why explicitly, no, you're not required to know how to do it. But you are meant to know what it is. And that's why, whereas beforehand, not only were you meant to know what it is, and then how. So they'll give you a graph and they'll say, by the main of the x's, what's the domain of range? So you're not required to do that.
Domain of G, domain of it. This is range.
What happened? Alright. Here we go. Let's have a look. A. Hopefully you got the range of f as all real values except 0. Domain of f is all real values except 0 again. And then you got range of g, which is equal to 0 to infinity. So r plus union 0. And then you've got domain of g, which is the square root function. Square root function, the domain is from 3 to infinity. That's part A. Anyone had difficulties with that one? No? B. Which one of them exists? So, the only way to know is if it's f of g, what's the conditions again? If it's f of g, it means I'm substituting g into f of x. Okay, so if you write it out, this is the same thing as saying f of g of x. So what's the condition? Range of what? Good. Range of g has to be a subset of the domain of f. Okay, because in this case here, you're substituting g of x into f of x. So g of x is the range. And so you already figured out from part A, range of g is 0 to infinity. Your question, is it a subset of the domain of f, which is r excluding 0? Is that a subset? No. Why is it not a subset? What's the issue? The 0. Okay, the 0 is the problem. If you draw a number line, the first part says include 0 all the way to infinity. So let's say that's 0. Whereas the second part says all real values but not 0. So technically you got this. That's not a subset. It's all a subset up until 0. Okay, so you know that this is not defined. Okay, then you go to g of f, which is the other way around. You're now saying in g I'm substituting f of x. In this case, that would mean that the range of f needs to be a subset of the domain of g. We already read it out from part A, so range of f, which we have r excluding excluding 0. Is it a subset of the domain of g from 3 to infinity? Is that a subset? No. Okay, so neither of them. Neither of them exist at the moment. Okay? Because that's... Yeah. So it means for both of them, you have to change the domain. Okay, now the first part is easy. F of g, the only thing you have to change is to not have a range of 0. Okay, so if you look at this graph here, if you don't want, so a range of g, which is this one, the only way not to have a range of 0, which means you have to change the domain here. Now, how are you going to get y equal to 0 for g of x? It's when x is equal to 3. If you didn't know that, you can sub 0 in and try to solve when will you get a range of 0, because that's what you want, right? I'm going to do it in blue here so you can see. When will you get 0 for the range of g? The only time you're going to get that is when the range of g is 0. 0 equals the root x minus 3. You can think about it visually, or you can do it algebraically. Square both sides, and you get 0 is equal to x minus 3. Solve for x equals 3. So when x equals to 3, y equals 0. But I don't want y to equal to 0. So that means your domain now changes. Instead of including 3, it is now not including 3 to infinity. Okay? And that's part C, and I've just figured out part C. Restrict the domain so that it does work. That's what I've done. The new domain for G, domain of G, if it was not including 3, so that means in your number line this was an open circle, that would change things. If that's an open circle, then I now have not including 0, and that's a subset. Okay. And if you were to do G of n, what's the issue? It says that I want it to be 3 all the way to infinity, but this is all real values except 0. So I need to restrict this graph up, at least up to from 3 to infinity to make it a subset. So the question is, when will your range of f, which is your rectangular hyperbola, when will it be 3 and onwards? So you look at the graph. That's why I'm saying methods is all about visualization. This is your rectangular hyperbola. You want the range to be 3 to infinity. Say from 3 to infinity is up here. I'm going to highlight it. 3 to infinity is this axis. So that means I only want this part of the graph. That's the only part. So the question is, I don't know what that x value is to get a range of 3. So how do you figure that out? Sub 3 in. Figure out for x. And if you do that in sub 3, switch the x in 3, then becomes 1/3. So I know when x is a third, okay, I will get 3. And it's okay because I wanted 3. 3 all the way to infinity. So I need from 1/3 for the x-axis. I'll do it in red so you can see here. I'm saying, whoops. I want in red. I've got this here at this point. X has to be a third. Now if you were to write the domain for the highlighted section I only want 0 to infinity, 3 to infinity. What's my domain? What's my domain? domain. Yes. Not including 0 all the way to 1 and 3, but inclusive. Okay, because this is an asymptote there, because we only want that section. Whereas over here is all negative. So if I only want that section, not including 0, the graph will keep going and going and going, all the way up to including 3. If that's the x values, then the range will be 3 to infinity. Okay. That's the 3 infinity of a 1 on an x graph. 0 to 3, 0 to 1/3 is the domain, and so your y values will be including 3 all the way to infinity. So answering that second question, if I change domain of f, which I'll put a star, that's the new domain. It has to be from not including 0 to 1/3 inclusive. Okay. Instead of R. Okay, so instead of having domain R, that's a problem because R will tell me everything. But that's not what I want. I don't want any negatives here, and I don't want any of these sections here. I only want range from 3 to infinity, so I need this section. So what I'm changing is I'm changing that. Changing that to get from 0 to 1/3, I should get only y values above. Okay. And that's possible. That's the hardest part. See, out of all the things I've just done so far, it wasn't the first part, it wasn't the second part, it was the third part. What was hard about the third part, it wasn't this one either, it wasn't f of g, I purposely made it g of f. Okay, g of f was the one that was tricky because now you have to really understand that you're working the domain to change the range. Okay? But then after that, answering the last two questions is easy. Find the domain of f of g and g of f if they exist. These are the domains of f, that's the domain of g. I can't remember where I wrote it. I wrote it over here. Domain of g. Those are the ones that will work. Those are the ones that will make the composite functions exist. And those are your two answers. You've done the hard work. Okay? That's your answers. Students who leave it blank after they've done C only tells me that they don't understand what they're doing. Okay, but the hardest part here is understanding C. How do we feel? It's all right. That's 7B. Okay, so if you find composite functions tricky, 7B is another practice for you to go back. Okay. And then finally, inverses, which we've done so much of, and I think most of you are pretty good at it now, but let's revise. Inverse functions. Whoops. No, I just gave you the answer. Let's go. I was going to ask, there's only one skill that examiners always test you for inverse functions. What must you have for an inverse function to exist? It has to be a one-to-one what? Function. Okay? In order for you to have an inverse function, not inverse relation, inverse function can only exist if you have a one-to-one function. If they ask you that, yeah, then inverse relation will be almost anything. That is a many-to-one, anything. Okay? Next one. Is this an example? Yeah. So you got first thing you needed to know, inverse function can only exist if it is a one-to-one function. Okay? Second part, once you know that you can have an inverse function, what else does it also change? What's the other thing you need to know? Good. The domain of the function becomes the range of the inverse. The range of the function becomes the domain of the inverse. Okay? That's the second part. But then there was also one more from your SAC. One more extra skill. That you can either do it without knowing this idea. Makes it hard.
Reflection in the y equals x.
Okay, because it's a reflection of y equals x, how does that help us? Say it again? You switch the y and an x, which gives you this domain of function, which is the inverse. That's okay, but I'm looking for something else. Something in your SAC that a lot of people weren't doing. There was only like a handful in 2 of my classes. Good. When do you do that? When you? Not finding the inverse?
Writing before -1 function.
No. No, so Daniel said, yeah, it is one of the things, but there was another part that a lot of students weren't doing. When you're solving for the...
Transformation.
No, okay, I'll tell you.
No, say the question first.
No, there wasn't the question. I was asking, do you remember what it was? When do you use something to do with y equals x? And Daniel said it that when you equate it to equal to x.
Yeah.
When do you equate it to equal to x? How do you know when you're going to do this?
Oh, when they meet.
When they meet. When you're solving for the intersection of f of x and the inverse function. Remember, in your SACs, there were questions where they said find the last SAC that you did, where they said find the intersection of your f of x, your function, and your inverse. So you sketched the function, so it could have looked like that. And then you sketched your inverse, which is something like, I can't remember what it was. Something like this, maybe?
Disgusting.
I can't remember what I just remembered you had a rectangle.
Oh, yeah,
The area of the rectangle, yeah?
I remember.
You had those two shapes, but they were actually no, it can't look like this. It had to intersect. It had to intersect.
It was a translation of 3 units.
Yeah, it had to intersect. Now, what you were required to do was to find the intersection of f of x and inverse. Now, this is what most of you did.
Yeah.
And what you found, as most of you were doing, it was either your algebra section was really good and you were able to solve it, or it was so tedious. It was a massive, lot of work to do with a lot of unknowns. Yeah?
Yeah.
So, the tip was instead of doing, so let's say, sorry, I'm trying to rub this.
I used to type it in the chat.
Yeah. Instead of trying to do solving f of x, because it said solve algebraically, instead of doing your function, let's say x squared, and then equating that to root of x, and trying to, this one's easier, but if you had an exponential or hyperbola, it was difficult to do. The easier way to do it was because you know they are getting reflected along the y equals x line, so where they meet, where they intersect, has to be right at y equals x. So instead of saying f of x equals to inverse, you can actually say it equal to x. You can do that. And that's a much easier way to solve. Okay, so that's where a lot of people were doing. They were doing the inverse, and then you put it together. It was a massive equation. It was much easier to just equate it to x, because we're saying f of x, which is y, that's your y. You can equate it to the inverse if you want, or the inverse and the actual function has to intersect right at the reflection. Because, you know, if they reflect from here to here, like from here to here, then what about at the point that they meet? It has to be exactly the same. It's y equals x. And that's the third point examiners will use, because a lot of students forget that. So we all know one-to-one function, they'll test that in your multiple choice. Domain and range, that depends on most students, exam 1. And then finally, the third part, when you're solving y equals x, don't forget that point. Okay? You can solve for the intersection by letting it equal to x. It's much easier to solve than trying to do it with the inverse. Okay? And that's it. That's 7b. I'll leave you guys to it. That's 7b. Those are the 3 points I want you to take out of inverse. Composite functions, it's part C to get your head around. Do you want to do the test a bit early? Why are you tripping?